A star initially has 10 power 40 deuterons. It produces energy via the process 1H2 plus 1H2 giving 1H3 plus P and 1H2 plus 1H3 giving 2He4 plus N. If the average power radiated by the star is 10 power 16 watt, the deuteron supply of the star exhausted in time of order of option A 10 power 6 seconds, option B 10 power 8 seconds, option C 10 power 12 seconds. The masses of the nuclei are as follows. Mass of H2 2.014 AMU, mass of neutron 1.008 AMU, mass of proton 1.007 AMU and mass of helium 4.001 AMU. Now here we are given two equations. First equation 1H2 plus 1H2 giving 1H3 plus P and second equation 1H2 plus 1H3 giving 2He4 plus N. Now adding these two equations we get the final equation as 3 1H2 giving 2He4 plus N plus P. So this is the reaction through which the deuteron is exhausted. Now we know that the mass defect is equal to delta M is equal to 3 times mass of proton, 3 times mass of deuteron, 3 into 2.014 minus 1 times mass of helium, that is 4.001, minus mass of neutron, that is 1.008, minus mass of proton, that is 1.007. So we have delta M is equal to 0.026 AMU. So if we know the delta M value, then we can calculate the energy. Now we have energy is equal to, we have delta M into 931. So this is equal to 0.026 into 931. So we have it as 3.87 into 10 power minus 12 joules. So this is the energy radiated in the process. Now we know that this is the energy radiated for 3 neutrons. So for 10 power 40 deuterons, we have energy E is equal to 10 power 40 divided by 3 into 3.87 into 10 power minus 12. So this is equal to, E is equal to 1.29 into 10 power 28 joules. So this is the energy radiated by the process. Now we know that the power radiated in the process is equal to 10 power 16 watt, which is equal to 10 power 16 joule per second. Now if we know the power radiated and the energy, then we have time T is equal to energy divided by power, that is equal to 1.29 into 10 power 28 divided by power is 10 power 16. So this is equal to 1.29 into 10 power 12 seconds. So the time is of the order 10 power plus 12 seconds, and hence option C is the correct answer.
Hi, the question is, in a statement first, in a spontaneous fusion reactions, a heavy nucleus is split into two medium-sized ones. Each of new nuclei will have more binding energy per nucleon than the original nucleus. First statement, and the second statement is, joining two light nuclei together to give the single nucleus of the medium size means more binding energy per nucleon in the new nucleus. Clear? Now, if we talk about the first statement, so if we draw the graph of the binding energy per nucleons, so we can draw the graph, then we can analyze. So let us consider this, and at this is the binding energy per nucleus. Binding energy per nucleus. This clear? Now graph is like this. So we can see the graph is like this. So from here this, and this is what fusion, this is fusion, and this is what fission. Fission. So we can see that when the heavy nuclei break and it convert into the two small nucleus. This clear? Now we can see that when the parent nucleus is break into two daughter nucleus, so this let us consider this is the parent nucleus, and it break into the two daughter nucleus, and this plus this. So let us consider this is the D1 and this is what D2, and this is what parent nucleus, and this is equal to some amount of the energy Q value. Clear this? So what is the Q value? We can see from here. Q value is what? Q value is the binding energy of this daughter nucleus. So this is the D1 and D2 we can assume. This is what D1 and D2. This is the D1 and this is what D2. So this Q value is equal to binding energy of D1 means the outer one we can assume. This is the D1 value. So this is what D1, and plus we can write binding energy of D2 and minus binding energy of this parent nucleus. So from here we can see that this is equal to this Q value is greater than 0 because this is the continuous spontaneous reactions. It is given that this reaction is what? Spontaneous fusion reactions. Heavy nucleus is split into two medium sized ones. Clear? So from here we can see that each of the new nuclei will have the more binding energy. So we can see that here the daughter nuclei has a more binding energy, we can see, because this is the spontaneous reaction. So this Q value is the greater than this, greater than 0. So this D1 binding energy of the D1 plus binding energy of D2, this is the greater than this 0. So we can see that this statement is the correct statement. Clear? So this statement is the first statement is the correct statement. Now coming to the second statement. Joining two light nuclei together to give the single nucleus of the medium size means more binding energy per nucleus in the new nucleus. Clear? So from here we can see that this statement is not always true. Second statement is not always true. The main factor is what? N by P ratio. So this ratio is main factor. Clear? So this ratio we have to adjust for the reaction. Clear? So we can see that for second statement we can see that this is not always true, that the joining two light nucleus together to give the single nucleus of the medium size means more binding energy per nucleus in the new nucleus. No, this statement is not always true because of N by P ratio should be adjusted for this reaction. Clear? So we can say that second is the wrong statement. So we can say that from option we can see that statement 1 is true and statement 2 is the false. Clear? Hope this answered your question. Thank you.
Hello everyone, let us start with our question. In this question, what is given that the masses of the nucleus X, A, Z is less than the sum of the masses A minus Z, number of neutron, and Z is the number of proton in the nucleus. Now the energy equivalent to the corresponding mass difference is known as the binding energy. Okay, that means the mass difference would correspond to the binding energy of the nucleus. Now if there is a heavier nucleus of mass M which break into two lighter nuclei M1 and M2 only if M1 plus M2 is less than M. That means if this is a heavier nuclei, this is a heavier nuclei. If you want to break it into smaller nuclei, okay, so this is having a mass, let's say this is having a mass capital M and this is a mass M1 and M2. Now this could only happen, okay, this breaking could only happen if M1 plus M2 is less than M. Also the two lighter nuclei of mass M3 and M4 can undergo complete fusion and forms a heavier nuclei only if M3 plus M4 is greater than M. That means the mass of the nuclei is greater than the M dash. Now what does it mean? It simply means that these are what? M1 plus M2 in this expression, these are the, we can say that reactant. And what is this? This is the product. This is our product, the product which is formed. And this is our reactant. Now in the second case also we can see that M1 plus M2, these are fusing. Okay, these are fusing, so these would be the reactant. And M is the final product which is formed. So we can say that the reaction could be possible if the mass of the reactant is greater than mass of the product. Okay, this we should remember. From the above, the passage which has been given, we can just conclude this. If mass of the reactant is greater than the mass of the product, then the breakdown or the fusion is possible, otherwise not. Now we need to check which of the statement is the correct statement. Now in the A statement, it is given that nucleus of the lithium can emit an alpha particle, whether it can emit or not. So we say that A, in the A option, lithium, it would be 6,3. Now if it emits a alpha particle, it would be this, the helium atom. Okay, So what would be the remaining portion here? It would be, so we can say that 6 minus 2 would be 2 and 3 minus 1 would be 1. So it would be a deuteron. Okay. So this would be the case. Now, if you put the masses of this lithium and if we just subtract the masses of this hydrogen and the deuterium, then we can get the value. So delta M would be equals to. So for our lithium, we have been given with the value. So we can check the value of lithium has been given and the value of helium have been given, and this is also given. Now, if we put all the values, so it would be equals to 6.015123 minus the masses, sum of the masses here. So it would be 2.014102 plus 4.002603. These are the masses. Now, if we calculate this value, it would turn out to be minus 1.5 into 10 raised to the power minus 3. So this would contract this. That means this is not possible because this reactant is not greater than the product sum of the masses. Now, if we check for the B option, it is given that this can emit a proton. So we just write, first of all, we just write the equation. So this is the polonium 210, then 84. Now our proton would be just 1H1. This would be our proton. So if we just subtract 210 minus 1, it would be 209. And this would be 84 minus 1, it would be 83. Now 209, 83, this would correspond to BI. Okay. So this would be our BI. Now again, if we just take the similar case, if we just subtract the masses of the reactant from take the difference of this mass and this mass. So we get the mass value. So it would be 209.982876 minus. So these values are given in the above table. Minus mass of this, so it would be 208.980388 plus mass of this proton, or we can say that 1H1. So it would be 1.007825. Now, if we calculate this clearly, we can see that this value would be greater than this value. And the answer, if we calculate, it would turn out to be minus 5.3 into 10 raised to the power minus 3. So this is also coming in negative. So this is also not possible. Now, if we check for the C option, it is given that deuteron and alpha particle fuse to can undergo complete fusion. So we take a deuteron, so it would be this, plus alpha particle, it would be this helium 2H4. Now it would convert to Li6. Okay. Now if you put the value, if we take the delta M, the reactant minus the product masses, so it would be 2.014102 plus the mass of this alpha or helium 4.002603, then minus the mass of the lithium 6.015123. Now if we calculate this, this would turn out to be 5.38 into 10 raised to the, 1.58 into 10 raised to the power minus 3. So this is coming out to be positive. That means C is possible. So our option would be C option. Now similarly, if we calculate for the last one, so this is Zn plus Se undergoing a complete fusion reaction. For the D part, we just write the equation first. So this is the equation, Zn fusing with Se. So this is 70 and 30. For Se, it is 82, 34. So if we just take the product, this sum of the this atomic this mass number, it would turn out to be 152 and 64. Now this is also given in the table. For this part, if we calculate our delta M, again it would turn out to be negative. So it would be 0.077. So this is also negative. That means this is also not possible. So the possibility is just the C option. Hope you understood the solution. Thank you.